Hello, learners. With you here is Mwalimu Zakaria. Welcome to my YouTube channel, Math Chem Mastery. Here are my contacts, both phone number and email. I do tuitions, both physical and online tuitions, both Kenya system and British system. Today we have chemistry from 3 work. Topic 1, Chemistry of Gas Laws. Let's consider lesson 1. That is our lesson for today. We will record the video lesson by lesson. We will discuss lesson 1, lesson 2, lesson 3 until the topic ends. We have matter exists in 3 states, namely solid, liquids, and gases. I think you know the definition for matter is anything that has a mass and occupies space. Also, you remember the interconvertible state of matter. We have the solid to the liquid to the gas. So each state from solid to liquid, melting, liquid to gas, evaporation, from gas to liquid, condensation, from liquid to solid, freezing. Also direct from solid to gas, sublimation. There's another question that asks about sublimation state, or to give example of sublimate substance. So matter exists in 3 states, namely solids, liquids, and gases. A gas is a substance that do not have a fixed shape or volume and whose particles are far apart. Gas laws focuses on the property of matters in gaseous state, because the state of matter we have solid, liquid, and gases. In the topic of gas law, we'll consider now the state of matter that is in gaseous state. NB, we have NB1. Gases occupy any available space. What is the reason for that one? This is because gas particles are made up of small, teeny particles which are always in continuous random motion as they possess kinetic energy. So many gases occupy any space, any available space. Why? Because the particles are made up of tiny particles which are always in continuous motion and they possess the kinetic energy. Second, gases have free movement. Why? The free movement of gases is possible because the atoms or molecules have weak intermolecular forces, that is the weak van der Waals forces of attraction between them. So they move freely. Why? Because the force of attraction that holds between them, it is very weak. The intermolecular force of attraction is the one that holds between the gases. We have note gas laws are affected by 2 physical conditions. What is it? We have temperature and pressure. Mostly gas law, also the Boyle's law, Charles' law, and the combined gas law are affected by the temperature and pressure. In order to explain the behavior of the gases, it is important to understand the interrelationship between volume, pressure, and temperature of a fixed mass of a gas. Let's talk about gas laws. This topic of gas laws include Boyle's law, Charles' law, combined gas law, and Graham's law of division. Mostly to know the difference between Boyle's law, Charles' law, and combined gas law, we must know something called variables and constant. We have 2 things. We have variables and we have constant. Why? Because the 3 factors which affect or the interrelationship is volume, pressure, and temperature. If we have Boyle's law, volume and pressure are the variables. So volume and pressure are the variables. What is constant? The temperature is constant for the Boyle's law. So the factor that affect volume, pressure are the variables for the Boyle's law, while temperature is constant. For Charles' law, volume and temperature are variables. Variables are the one which affect now the gas, while pressure is constant. The pressure in Charles' law is constant. So out of volume, pressure, and temperature, volume and temperature are the variables, while pressure is constant in Charles' law. Combined gas law, all are variables. We have the volume, we have the pressure, and we have the temperature. All of them are the variables, meaning they affect the combined gas law. And also we have the Graham's law of diffusion. We will see that one, the factor which affect. Next, let's start now with our first gas law, that is the Boyle's law. We see the Boyle's law, the first gas law that we have. We discuss it now deeply. Now, for us to know the gas law, we must know 5 things. We must know 5 or 6 things. First, let's know definition. The definition of Boyle's law, because every topic and every subtopic have aim. So by the end of this lesson, we must know each one of it. So the first thing we'll consider definition of Boyle's law. Second, we look molecular explanation of Boyle's law. Molecular explanation of Boyle's law. Thirdly, we look on the graph of Boyle's law. The graph of Boyle's law. The graph of Boyle's law, how it look. That's what we'll see. Fourth, we will look implication of Boyle's law. Implication of Boyle's law. How is Boyle's law? How it implies. Implication of Boyle's law. Fifth, we will look on mathematical expression of Boyle's law. How Boyle's law is expressed mathematically. That is next what we will look. So we'll look mathematical expression of Boyle's law. And fifth, and the sixth, we will look application of Boyle's law. How do we apply? In here, mathematical expression of Boyle's law, we will derive the formula of the Boyle's law, and that formula is what we will apply to solve the application question. Applications of Boyle's law. So by the end of this lesson, we should know all of them, the 6 of them. Let's look at definition of Boyle's law. How Boyle's law is defined. The law states that the volume of a fixed mass of a gas is inversely, or you can refer indirectly proportional to its pressure. Remember, we have said for Boyle's law, the variables that affect are volume and pressure. So the volume is inversely proportional to the pressure. What is constant? The temperature is constant for the Boyle's law at constant temperature. That is now definition of Boyle's law. It is stated that the volume of a fixed mass of a gas is inversely proportional to its pressure at constant temperature. Second, let's look molecular explanation of Boyle's law. We have 2 experiments here. We will confirm from these 2 experiments how we can explain Boyle's law molecularly. We have a syringe here. The syringe here is the handle. The outer part of the syringe is called the barrel. The one that push inside is called the piston. And here we put now the finger. We have put now at this end the finger. These are the start, and here we have at the end. At the end, you see the volume here. We have a big volume, and we have here a small volume. There's a finger that is put there. We have a question here. What happens to the volume of air as the piston is pushed in? Now, let's say you hold on this piston on this side. So as you push this piston inside, what happened to the volume of air? Meaning here, we assume that the volume is bigger. The volume here became what? The volume here is small. So what happened to it? Let's see the answer. But now from the figure itself that we are saying, the setup, we see the volume here, we had a bigger volume. And here we have a small volume. So meaning the volume here is decreasing. Let's confirm now our answer. As the piston is pushed into the barrel, the volume of the fixed mass of gas reduces, meaning the volume reduces. While here we have bigger volume and here we have smaller volume. The gas exerts more pressure on the finger, and the finger that is put here, you feel now more pressure exerting on it. So why? Because as you push the piston here, as you push the piston inside, the volume is pushed now outside from the cylinder. Now as the volume is pushed outside, you exert now more pressure at the part of the finger. Second question, explain why when the volume of a fixed mass of a gas is decreased, the pressure of the gas increases. Like this one here, as we push here, the volume decreases, the volume becomes smaller, but the pressure that we see at the finger increases. We explain now what we have seen here. Why? We want to explain now. When the volume is decreased, the pressure increases. Why? I want to say now that one. This is because gas molecules are confined to a small space. Hence, the gas molecules have to cover a shorter distance before colliding with the walls of the container, causing an increase in the rate of collision between the gas molecules and the walls of the container. Meaning now this space that we have here, it is small. As we push now the piston inside, the gas covers a shorter distance before they collide now with the walls of the container that we have, the walls of this cylinder that we have, and that causes increase in rate of collision between the gas molecules and the walls of the container. So due to the rate of increase, now that rate increases result to an increase in the pressure while the volume decreases. The opposite of this question, we have explained why when the volume of a fixed mass of a gas is increased, here is the volume is decreased. If the volume is decreased, we are saying the pressure increases. What about this one? A fixed mass of a gas is increased, the pressure of the gas decreases. So we increase the volume, we are saying here now the pressure decreases. Why? What is the reason? This is because gas molecules are confined to a large space. Here they are confined to a small space. It is opposite of this one. It is a small space. This one is confined to a large space. Hence, the gas molecules have to cover a longer distance. Here, the gas molecules have to cover a shorter distance before colliding with the walls of the container, causing a decrease in the rate of collision. Here, it was causing an increase. If the rate of collision increases, that is why now the pressure was increasing. Here, the rate of collision is decreasing. Also, the pressure decreases. So it covers a longer distance before colliding with the walls of the container, causing a decrease in the rate of collision between the gas molecules and the walls of the container. And that is how we find out the molecular explanation of the Boyle's law. Thirdly, let's see the graph of Boyle's law. We are done with the molecular explanation. We go now to the graph of Boyle's law. Now, one thing that we should know, for us to know the graph of the Boyle's law, the graph of Boyle's law. Let's consider this one. Boyle's law, the normal graph of Boyle's law, when it is drawn, it is a curve. How does this graph is obtained? Is graph of pressure. Is a graph of pressure against a volume. So it is a graph of pressure against the volume. Second, also for Boyle's law, it gives us a straight line graph. It gives us a straight line. How does the straight line gives? This is graph now. The graph of pressure. The graph of pressure against against reciprocal of volume. So Boyle's law always give us two kind of graph. The first graph of Boyle's law, that is the normal graph of Boyle's law, it is curved. It will be straight line when the graph is plotted against the reciprocal of volume. This volume, the reciprocal of this volume, when it's plotted, it gives us the graph. But the normal curve, the normal graph of Boyle's law, it is the curve. That is the graph of pressure against volume, and we have it here. The Boyle's law assume below. One, we have a curve. This one is a curve. Why is it a curve? Because we say it's a graph of pressure against the volume. Everything that comes before the against is the line of y-axis. After against is the line of x-axis. So here you are seeing the pressure is the line of x-axis, the y-axis, while volume the line of x-axis. And this is the graph that we have, the curve. The second graph is this graph, which is a straight line. This is a graph of pressure against reciprocal of volume. Pressure and volume give you curve. Pressure and the reciprocal of this volume will give now a straight line. And these are the graphs of Boyle's law. Fourth, let's see implication of Boyle's law. What Boyle's law implies. What does it imply? How does it imply? We have it here. Boyle's law implies that as pressure increases, as the pressure increases, the volume decreases, and vice versa. Meaning, if the volume increases, the pressure decreases. So we have this illustration. Let's say here we have this triangle. We have volume. We're seeing big volume is becoming smaller. The volume is becoming smaller. If the volume decreases here, what does the temperature doing? Let's see here now the illustration for the Boyle's law that we have. Here we have now the volume. We are saying now the volume decreases because the Boyle's law implies that if the pressure increases, the volume decreases. If the pressure decreases, the volume increases. So it is vice versa to each other. So here we have volume decreasing, volume decreasing. So if the volume decreasing, what happened to the pressure? Pressure. You're saying the pressure is increases. If we look from this side, the pressure decreasing, it's decreasing the pressure. What happens to the volume? The volume is increasing. That is now what the Boyle's law implies. As pressure increases, the volume decreases, and vice versa. Fifth, let's say now mathematical expression of Boyle's law. How do we express Boyle's law mathematically? Now, one thing that we should know, when we're defining the Boyle's law, we say this is a gas where a fixed volume of a fixed mass of a gas is inversely proportional to the pressure. So we can get here the volume that we have, the volume of a fixed mass of a gas is inversely proportional to the pressure. This is a sign that we use now for proportional. Let me use now the state. Let's say volume is for V is inversely proportional to 1 of P, that is for pressure. So let's introduce now constant K here. Introduce the constant K. If we introduce constant K, what happens? This sign changes to equal, so volume is equal to K over P. We multiply here by P, I multiply here by P, so by P. So PV is equal to K. How do we compare? Let's say when we're comparing now two gases, how does the Boyle's law shows comparing of two gases? Because this is the formula of the Boyle's law now. We have PV, but comparing to two gases, the general expression now, or the general formula. I'm referring now the general formula of Boyle's law when we compare now to two gases, it be P1 V1, because the formula is PV is equal to P2 V2, and this is the formula that we use to solve application questions of the Boyle's law. P1 V1 equal to P2 V2. That is now mathematical expression of Boyle's law. Always the Boyle's law states that the volume of a fixed mass of a gas is inversely or indirectly proportional to the pressure. We have introduced now the constant K. We have V equal to K over P by B, so PV become K. How do you compare two gases? This is for the gas 1 and this one is for the gas 2. The two gases have pressure and volume because the variables that affect the Boyle's law is pressure and volume. Let's say now application of Boyle's law. Before we look now the application of Boyle's law, let's know now the units that are used, because we have units and it is very important for us to know for the Boyle's law which unit affect the volume and which unit affect now the pressure. The unit that you can see for volume is affected by centimeter cubic, volume is affected by liters, volume is affected by liters, volume is also affected by meter cubic. And one thing that we should know, the SI unit, the standard unit of volume, it is meter cubic. Some questions in the Boyle's law you can be told when you get the final answer, you can say express the answer in SI unit. So if we are finding out that time volume, the SI unit of volume is meter cubic. What can we have for pressure? Pressure, we have atmosphere, one unit that we use to measure pressure, atmosphere, which we abbreviate as ATM. Another unit that we have for this one, it is millimeter mercury. Another one, it is the pascals, which we abbreviate as PE. And also the SI unit of pressure, it is Pascal. The SI unit of pressure, it is Pascal. So if you want to compare this SI unit, if I'm dealing with meter cubic, how can I know now? 1 meter cubic, always 1 meter cubic is equal to 1 million centimeter cubic. If we see the Pascal, always the combination now of the units of pressure. We have atmosphere, we have millimeter mercury, we have the Pascal. So for this one, always for the pressure, we normally say 1 atmosphere is equal to 760 millimeter per mercury, which is equal to also 1.01325 times 10 power 5 Pascal. So you can use sometimes if the question asks you to change the equation of pressure in SI unit, the SI unit for pressure, it is Pascal. So if you have atmosphere, you can compare now. 1 atmosphere is equal to this one. 760 millimeter mercury is equal to this Pascal. And this is now the units, the important unit that we have in the Boyle's law, both the volume and the pressure. That is now the application of Boyle's law. Let's say now question. Let's solve now a question using this application part for the Boyle's law. Let's see question 1. Let's solve this question now. Now for this question, let's read it clearly. We have a volume of 375 centimeter cubic of a gas has a pressure of 20 atmosphere. Let me reduce now my space here. I have what now? I have a volume. Let me take this one as my volume 1. My volume 1, it is 375 centimeter cubic. Occupies a pressure, that is my pressure 1, equal to 20 atmosphere, that is ATM. What will be its volume? We don't have volume 2, tona is what we are looking. What will be its volume? So what will that volume be? That is the volume that we are looking. If the pressure is reduced to 15 atmosphere, meaning if the pressure is reduced to 15 atmosphere, meaning our pressure 2, it is 15 ATM. So what do we want to calculate here? We want to calculate now volume 2. So for us to calculate, we must remember now the formula for the Boyle's law. Boyle's law, the formula or the expression, we have P1, V1 equal to P2 and V2. Do we have P1? Yes, we have 20. That is 20 times V1, that is 375, is equal to P2, that is 15 times V2, which we don't have, which we are calculating for. So if we multiply 20 times 375, we have 20 times 375. What do we have? 7,500. So we have 7,500 is equal to 15 V2. Can I get the V2? Yes. We have 7,500 equal to 15 V2. So we divide with 15. We divide with 15 by 15 by 15. The volume 2 becomes what? So we have 7,500 divided by 15. And the volume 2, it is 500. So we have 500 centimeter cubic. That is now the volume 2 that we have. Now, have we referred now to the expression of the Boyle's law? Yes. Let's see now the implication. Boyle's law implies that if the volume increases, the pressure decreases. If the pressure increases, the volume decreases. So here we're having pressure. Our pressure here, it was 20. It is reduced to 15. So if the pressure reduces, it is vice versa. We expect the volume to increase. What have we get our volume here? We get our volume 500. So we have 500 here, the volume. So the volume, does it increase or the volume decreases? Decrease. The volume increases from 375 to 500. Why? Because our pressure was from 20 to 15. That is the implication of the Boyle's law. How the Boyle's law implies. Let's see the second question. We have a certain mass of a gas occupies for 50 centimeter cubic. So we have volume 1. We have a volume 1. It is 400 centimeter cubic at 30 degrees Celsius. We know the Boyle's law does the effect. So I think it is 30. It is 30 here. So the temperature is constant. Boyle's law, temperature does not affect. So it is constant. We'll write here, there is no need. And 730 millimeter mercury, that is our pressure. The pressure that I have, it is 730 millimeter mercury. Calculate the volume of the gas at 760. So we want to calculate what? The volume. So let's calculate the volume. Volume 2 do we have? We don't have. Is what we're calculating for. At a pressure of what? The pressure 2 that we have, it is 780 millimeter per mercury. Before we solve the question, let's see implication. We don't have volume, so pressure is from 730 to 780. The pressure increases. If the pressure increases, what do we know about the implication of Boyle's law? The volume will decrease. If pressure increases, the other one decreases. So the volume, we expect to get a volume which is less than 400. Let's solve this question. Let's use now the formula of the Boyle's law. Boyle's law says what? P1 V1 equal to P2 V2. What is our P1? We have 730 times V1, which is 400, equal to P2, which is 780 times V2, what we are calculating for now. Now let's multiply. We have 730 times 400 will give us a 292,000. 292,000 equal to 780 V2. Can we get V2 here? Over 780 over 780. 780, 780, we remain with V2. What is V2? We divide here with 780. We have 374.4 centimeter cubic. I think now our implication is right. We said we expect a volume which is less than 400, and we get the volume here 374. That is now the implication of the Boyle's law. But the question doesn't end there. Calculate the volume in where? In SI units. Are you getting? We have discussed here what is the SI unit of volume. If we come back to here, if we have volume, the SI unit of volume is meter cubic, and what we have here, it is centimeter cubic. So we need to change this centimeter cubic to meter cubic to the SI unit of volume. So 1 meter cubic is equal to what? Is equal to 1 million centimeter cubic. So we can write here. We have 1 meter cubic is equal to 1 million. 1 million centimeter cubic. What about what? What about 374.4 centimeter cubic is equal to how many meter cubic? So we can cross multiply. We have by centimeter cubic, we have 1 times 374.4 over 1 million. Of 1 million. So what are we going to have? We divide this one with 1 million. So what we have 3.744 times 10 power negative 4 meter cubic, and this is the volume that you have calculated. That is now from the Boyle's law. Now let's see here, go to question 3. At a constant temperature, a gas at 620 millimeter mercury, that is pressure 1, we have, I identify one by one. It is 620 millimeter per mercury, occupies a volume of 350. The volume that it occupies, volume 1, it is volume of 350 liters. The gas is to expand and occupy a volume, meaning our volume 2 is equal to 650 liters. With the question asking, what is the new gas pressure? We're asking now the pressure 2 in SI units, so we are asking now the pressure. I get it. Let's say now the implication of Boyle's law. Here we have a volume. Volume is from 350 to 650. The volume increases. If one increases, the other one decreases. So we expect now the pressure that we are going to be here, that we are going to get, will be less than 620 millimeter mercury. Let's come now to the question. Let you know the expression of the Boyle's law. Boyle's law, it is P1 V1 equal to P2 V2. What is our P1? We have 620 times V1, we have 350 is equal to P2. We don't have. What is our V2? We have 650 times P2. So let's multiply 650 with 620 with 350. We have 620 times 350. We have 217,000 is equal to 650 P2. Let's get P2 over 650 over 650. So 650. Our pressure 2, we multiply this one with 650. We have what? That 333.85 millimeter mercury, because we had millimeter mercury here. So we get now right our implication. We say the volume increases from 350 to 650. We expect the pressure to decrease. Our pressure was 620, it is decreased to 333.85, and that is how we imply now for the Boyle's law. But the question doesn't end there. Write the pressure in SI units. So let's convert now the SI unit to pressure. Do you remember the SI unit of pressure we have discussed right now? So here the unit for pressure, it is atmosphere, millimeter per mercury, and Pascal. So the SI unit of pressure, it is Pascal. So how do we compare now to the 3 pressure? Always we said 1 atmosphere is equal to 760 millimeter per mercury, which is equal to 1.01325 times 10 power 5 Pascal. So our volume here, it is millimeter per mercury. We want to convert to Pascal. So let's say we have 760 millimeter mercury. It's equal to 1.01325 times 10 power 5 Pascal. What about 333.85 millimeter per mercury? It be now in Pascal. How much? So by millimeter per mercury. So you have 333.85 times 1.01325 times 10 power 5 over 760. So let's multiply and we get our final answer. We have 333, we multiply with 1.01325 times 10 power 5. We divide with 760. So what is our pressure? Our pressure, it is 44,509.16 Pascal, and we have expressed our pressure into the SI unit of pressure. Next, let's see next question. Let's see a question of KCC. We have a graph here. Sorry, I didn't draw the graph, but we have this graph show a fixed mass of a gas at constant temperature. So this is a graph that we have. Let me sketch here. So here we have the volume, and here we have the pressure. So we had a curve here, that is a graph, that is case C 203 paper 1. Now, what is the relationship between the volume and the pressure? What are you saying? Always for the Boyle's law, what we know that if one increases, the other one decreases. As we here, let's say we have a high pressure. If we have this high pressure decreasing, we are saying now the volume increases. So what is the relationship? We can say if the pressure decreases, the volume increases. That is how we can relate to them. So we say the pressure, if the pressure decreases, the volume increases. We can refer to that one now. If the pressure increases, we can have now the volume increasing. We have a last question here. 3 liters of oxygen gas at 1 atmosphere pressure were compressed to 2 atmosphere. So let's try to do. We have 3 liter, we have volume 1, we have 3 liters of what? We have pressure 1 at 1 atmosphere, that is 1 atm, were compressed to 2 atmosphere. Pressure 2, we have 2 atmosphere. Calculate the volume occupied, calculate the volume 2 that is occupying. So what do we have here? The implication, the pressure here is increasing. If the pressure is increasing, we expect now the volume to decrease. So let's write now the expression for Boyle's law. P1 V1 equal to P2 V2. What is our P1? It is 1 atmosphere times what is our V1 times 3 equal to what is our P2? 2 times V2. So 1 times 3, we have 3 equal to 2 V2. We can have over 2, we can have over 2. So our V2, it is 3 over 2 liters, which we can refer as volume 2 equal to 1.5 liters. So our liters now has decreased. It was from 3 liters to now 1.5 liters. Why? Because the pressure increases. The implication is that if one increases, the other one decreases. That is the implication of the Boyle's law. That is our lesson for today. We have here self-trial question. Try question 1 and question 2 and share the answer in the comment section. Welcome.